Hello everyone. In this video, I'm going to discuss solution of CSIR NET exam which was held today. So basically, I'm going to discuss memory-based questions and their solutions. This year or this year's paper or paper that was asked in this examination was some as a student told me that it was above average. I haven't seen the general aptitude part, but physics part I have seen, and indeed questions were not very simple. It required some अंडरस्टैंडिंग सम गुड अंडरस्टैंडिंग ऑफ फिजिक्स तो इसलिए हो सकता है कि एक्सपेक्टेड कट ऑफ जो है वो इस बार कम भी जा सकता है मतलब कट ऑफ विल नॉट बी वेरी हाई इट वुड बी अराउंड 80 फॉर जेआरएफ के लिए 80 के अराउंड हो सकता है कट ऑफ जनरल कैटेगरी में ठीक है सो लेट अस डिस्कस some memory based questions see this is a question from classical mechanics it's in this question Hamiltonian is given and Lagrangian was asked. So we can write this Hamiltonian as h equal to p square divided by 2, and in place of m we can write m e to the power plus x by a. Okay, this exponential I'm bringing down plus b of x. So we know that when we write Lagrangian, p square by 2m converts into half mv square, half m and v square. So therefore, when you write Lagrangian, see, there is a method, but I'm not using that method. I'm just directly writing like this. So in place of half, we'll write Lagrangian half, and in place of m, we have this factor. So m e to the power x by a, okay? And v square will be x dot square actually, okay? So basically, if there is e to the power minus x by a here, you will get e to the power plus x by a, okay, in Lagrangian. And if there is plus, then we will get minus. Okay, so whatever it was in question, okay, according to that, you can write here. And this potential, which does not depend on momentum, changes its sign. So it becomes v of x. So that will be the answer to this question. Okay, now move to another question. See, this question is related to electrostatics. There were two questions from electrostatics, I think. So in this question, you see, this is question says a long wire lies along z-axis. So there is a wire. I'm showing it by a dot here. Okay, so this dot represents a wire. Okay. Um, now this wire lies along z-axis, and suppose there is some point here which is at a distance rho. Yeah, let's call it r. We have to calculate suppose potential here v of r. So we know that this is on xy plane. Okay, this point is on xy plane. Here coordinate is x comma y comma 0. Okay, so we know that electric field of a long wire is given by lambda upon 2 pi epsilon naught r. Okay, so electric field is written as minus dv by dr. Okay, that is equal to lambda upon 2 pi epsilon naught r. So if you do cross multiplication, dv is equal to minus lambda upon 2 pi epsilon naught r, sorry, dr by r. Now you integrate it. So you get v is equal to minus lambda upon 2 pi epsilon naught, and this is ln r plus some constant c. So therefore, if you calculate potential at rho plus a, the rho plus a, so that will be equal to minus lambda upon 2 pi epsilon naught, and ln here rho plus a plus some constant c. And potential at rho will be equal to minus lambda upon 2 pi epsilon naught and ln rho plus some constant c. So take the difference. So v rho plus a minus v of rho, that is equal to, if you take difference, c will cancel out and you will get here minus lambda upon 2 pi epsilon naught and ln rho plus a and minus ln rho. So minus lambda upon 2 pi epsilon naught, and this is ln rho plus a and divided by rho. Okay, so now you can write it as minus lambda upon 2 pi epsilon naught, and this is ln 1 plus a by rho. Now we know that expansion of ln is written like this. See, I'll write here ln 1 plus x is something like this, x minus x square by 2. So, and other terms. So if you neglect higher order term, it will be just x. Okay. So in question actually, expansion up to 1 by rho was given only. So therefore, we will expand only up to first order term in A. Okay, so we'll get minus lambda upon 2 pi epsilon naught. And from here, you will get A by rho. So that is the answer. Okay. So that's the potential. Okay. Now move to another question. Question number 3. See, the question number 3 says, it's a question from classical mechanics. It says particle moves under potential V of r equal to beta r to the power k. Angular momentum of the particle was given. So question was, for a stable orbit, what should be the value of k and corresponding radius of the stable orbit? Actually, we know that when a particle moves under central potential, see, this is r dependent potential only. So this is a central potential. So when a particle moves under central potential, a stable orbit is actually circular orbit. Okay. So for circular orbit, it is easier to discuss such a situation. It is easier to use effective potential. So we'll write effective potential as V of r plus L square upon 2mr square. This is the effective potential. So V of r is beta r to the power k and plus L square upon 2mr square. Okay, this is V effective. Now for equilibrium orbit, or you can say stable orbit, equilibrium orbit. For equilibrium orbit, generally we have this situation, dV effective by dr at some r equal to r naught, that is equal to 0. Okay, so let's differentiate it and see what we are getting. So if you differentiate it, you get beta k and r to the power k minus 1 minus L square upon m r cubed. So we suppose we are calculating it at r naught, so we'll put r equal to r naught here, that is equal to 0. So from here you get r naught to the power k plus 2. Okay, that is equal to L square upon beta k or into m. That's what you get. So if you calculate r naught, you get here L square upon beta k and m, this whole power 1 by k plus 2. Now see here, if you put k equal to 2, we will get here r naught is equal to, if you put k here 2, L square upon 2 beta m, and here power 1 by 4. So if you in options k equal to 3 was also given. So if you put k equal to 3, then you will not get a value of r naught which was given in the option. Okay, so therefore if you put k equal to 2, you are getting this option, and this option was given. So therefore this is correct answer. Okay, so basically in other option, other values of k was given. So you put other values of k and you see whether you are getting the value of r naught which is given in the option or not. So that value of r naught we were not getting. Okay. All right. So now another question. See here. So I have done 3 questions. Now this is the 4th question. This is again a question from central force motion. So this, I think 3 questions were asked from central force motion. Okay. So this is also a question from central force motion. It says a particle moves under potential V of r is equal to this, its angular momentum is L. For a stable orbit, how k primed and L should be related. There was some relation given between these 3 things, and you had to tick correct option. Okay. So let's solve it. Solution. Again, question is related to stable orbit. So we will write V effective. V effective, that is equal to V of r and plus L square upon 2m r square. Okay. So now here V effective is equal to minus k by r minus k primed upon 3r cube and plus L square upon 2m r square. That is V effective. So now let's calculate again for a stable orbit. Derivative of effective potential is 0. So r equal to r by r not equal to 0 will write. So first derivative of effective potential is 0 for a stable orbit. So that's what we are doing here. So let's differentiate it. So what do you get when you differentiate it? You get here k by r square minus, sorry, plus k primed divided by r power 4. And here you get L square upon mr cubed. That is equal to 0. Okay. So now let us multiply both sides by r to the power 4. So you get here k r to the power. So if you multiply by r to the power 4, you get here k r square. And here you get plus k primed minus here you get L square upon M or into R, that is equal to 0. So this is a quadratic equation. We can rewrite it as K R square minus L square upon M or into R and plus K prime, that is equal to 0. Okay, this we are getting. So now if you calculate its discriminants, let's calculate the value of R. Okay, so R, if you calculate, you get here L square upon M plus minus root under B square. So you get here L power 4 by M square minus 4AC. So 4K into K primed. Okay, this you get, and divided by 2A. So this is 2K. Now to get real value of R, we must have L square by M square. Okay, minus 4K primed greater than 0. Okay, this must be positive, or at least it should be 0. Okay, so here we can say that 4K primed must be less than L square upon, sorry, L power 4 was there, L power 4 upon M square. Okay, so therefore K into K primed must be less than L power 4 by 4 M square. That is the correct answer. Okay, so such option was given. Okay, so you can take that option. Okay, now move to another question. It says a particle is, this is another question from central force motion. So there were 3 questions from central force motion actually. Okay, so a particle is moving in circle in this potential. So a particle is moving in circle. So we can write here, force acting in this direction, suppose its speed is v. So let us write radial equation of motion. So we'll write F radial is equal to mass into a radial. So let's put magnitude of radial force here. So that is K by R square. And here mass is M and radial acceleration magnitude is V square by R. Okay. So 1 R will cancel out. You will get V is equal to K upon M into R. Okay, under root. So that is the speed. Now question says suddenly force is changed from this value to this value. Okay, so therefore now if you write potential energy, you see potential energy will be F dr integration. Okay, so what you will get here is, if you put minus sign here, minus and minus will become plus, and K by R square integration will give you minus K by R. So potential basically becomes K by 2R. Okay, we are taking potential at infinity to be 0, so that's why we are not adding any constant. Okay, when you take potential at infinity to be 0, you don't have to add any constant. So here this is the potential energy now. Okay, and speed is this. See, when you change the force suddenly, its speed doesn't change suddenly. Okay, it's because to change speed, it requires some time. Okay, so therefore, if you calculate a total energy, you will have to write kinetic energy plus potential energy. So kinetic energy, we'll write half m and velocity square. So in velocity, we will use this velocity, which was calculated using previous force. So force was suddenly changed, so velocity doesn't immediately change. Okay, so velocity will change, but after some time. But we are doing calculation just after the force is changed actually. So therefore, half mv square you write, use this velocity, you will get here K upon m into R. Okay, and potential energy is this K upon 2R. So you can see here mm cancel, so you get K upon 2R, K upon 2R, that is 0. So when energy is 0 under this is actually 1 by R potential. So whenever energy is 0 under Kepler potential or 1 by R potential, path is parabolic. Okay, so the orbit is parabola. It is not always the case, but whenever potential is proportional to 1 by R, when potential is proportional to 1 by R and energy is 0, you orbit is parabola actually. Okay, so therefore correct answer will be parabola. So particle was initially moving in circle. So when force is suddenly changed to this value, particle will no longer be moving in circular path, it will go into parabolic path. Okay, now another question. See, this is a basic question. Okay, related to oscillation. It says a particle of mass m oscillates under potential, this potential. What is the time period of oscillation about stable equilibrium point? Okay, so for stable equilibrium point, this is for stable equilibrium point, we will write v primed at some x naught equal to 0. So when you differentiate it, you get 6 alpha upon x naught minus to the power 4, and here you get plus 6 beta upon x naught cube, that is equal to 0. So from here you get x naught is equal to alpha by beta. Now let's calculate second derivative at x naught. Okay, so when you calculate second derivative, you get here plus 24 alpha upon x naught to the power 5 and minus here you get 18 beta upon x naught to the power 4. So let's take x1 by x naught to the power 4 common. Okay, so you get here 24 alpha by x naught and minus 18 beta because we have taken x naught common. So when you put x naught here, alpha cancel out, so you get 24 beta minus 18 beta, so that is 6 beta. So here you get v double primed x at x naught is equal to 6 beta or divided by x naught to the power 4. Now you put the value of x naught here. So so you get here 6 beta to the power, when you put 4 beta to power 4 comes in numerator, so you get beta to power 5 and divide by alpha to the power 4. So that is the second derivative. So that is actually force constant. This is kx. So omega x will be equal to root under kx by mass. Second, when you calculate second derivative of potential at equilibrium point, and that comes out to be positive, it is called force constant. So that is it is coming out to be positive, so it is force constant. Now omega x angular frequency of oscillation is this much. So we'll put here kx is 6 beta to the power 5 divided by m alpha to the power 4. Okay, so omega is 2 pi by t. We'll write here 2 pi by t, and that is equal to 6 beta to the power 5 and divide by m alpha to the power 4. So therefore t is equal to 2 pi root under m alpha to the power 4 divided by 6 beta to the power 5. That's the answer. Okay. Next question. See, the question says for a state, this is the wave function given for a spin half particle actually. Okay. This is for a spin half particle. It is for electron perhaps, spin half particle. Okay. So here, so question says, what is the expectation value of total angular momentum? Okay. So total angular momentum. See, Lz, when Lz acts on this y Lm, this is Lm theta phi, this actually gives us mh bar. Okay, mh bar and y Lm. This is its eigenfunction. Okay, and similarly, when Sz acts on this chi plus minus, okay, it gives us plus minus h bar by 2. These are spin part of the wave function. Okay, chi is spin part of the wave function. Here we get chi plus minus. Okay, so these are eigenstate of Sz operator. Okay, so let's calculate. So when you calculate expectation value, basically you have to write like this, basically psi star. Okay, or we can write like this. Suppose as Lz operator plus Sz operator, and here expectation value with respect to psi. Okay, so when Lz acts on this one, it gives us mh bar, but m value is 0. So when Lz acts on this, we first term that we get is 0 actually. Okay, and it was given perhaps that this is normalized wave function also. Okay, now when Lz acts on this part, first we are calculating expectation value of Lz. So when Lz acts on this part, okay, this will give mh bar. Here m value is 1, so we will get h bar, f factor h bar. And since psi is multiplied from both sides, so root 5 by 8 will come twice. Okay, so we'll get here 5 by 8. Okay, 5 by 8. All right. Now let's calculate for Sz. So when Sz acts on this chi minus, it gives minus h bar by 2. Okay, but this 3 by 8 factor will be there. Okay, so we'll get here plus 3 by 8 and minus h bar by 2. Okay, minus h bar by 2 because of Sz. Now Sz acting on this gives us h bar by 2, but 5 by 8 factor will be there. Okay, 5 by 8, and here we get h bar by 2. All right, so now you can just calculate this. Okay, so if you calculate it, you will get perhaps 3 by 4 h bar. Okay, you can check it. This is what you are going to get. Now let's solve another question. See, this is See, the question is, a system has Hamiltonian. This is the Hamiltonian uh, for a system for which L1 is 1 and L2 is also 1. Okay. So now question is, calculate energy of the system. For this energy of system for L equal to 2, where L is total angular momentum. Okay. Total angular momentum quantum number. So we know that when you add L1 and L2, you are going to get L is equal to L1 minus L2 to L1 plus L2. So basically you are getting L equal to L1 minus L2. When you do, you get 0, and L1 plus L2, you get 2. So 0, 1 and 2. Okay. In interval of 1 you get. Okay. So these are the L values. So we have to calculate only for L equal to 2 actually. Okay. We have to do calculation for L equal to 2. See here, actually there are two angular momentum operator, L1 and L2, and L okay, so Hamiltonian is written in terms of two angular momentum operator. So we know that when two angular momentum are added actually, okay, then we have a set of commuting operators. And these commuting operators are L1 square, L2 square, and L square, which is actually total angular momentum, and LZ, total angular momentum Z component. So these are commuting operators. So we'll have to calculate actually expectation value of this Hamiltonian with respect to common eigenstate of these operators. Okay. So therefore, what we'll do is we'll write this Hamiltonian in terms of these operator. Okay. So H is equal to, we'll write like this, epsilon divided by H bar square. Okay. And here we'll get L1 dot L2. Okay. So L1 dot L2 and plus here you are getting L2 square and minus L1Z plus L2Z will be actually LZ. So LZ square. This is what we get. Okay. Now you see L1 dot L2 actually is written like this. L1 dot L2 is written like this. 1 by 2, and here you get L1 L square minus L1 square minus L2 square. This you all must be knowing. Okay. So let us put that here. Okay. So this is epsilon upon H bar square, and here we get L square minus L1 square minus L2 square and divided by 2 and plus L2 square and minus LZ square. Okay. Now let us calculate its expectation value with respect to common eigenstates of these operators. Okay. So we get expectation value to be equal to, here you will get L into L plus 1 H bar square. So H bar square will actually be common, and that will cancel this H bar square. So let us write like this. This H bar square will cancel out. So you'll get epsilon only. Here L into L plus 1. And here you will get minus L1 into L1 plus 1. And here you will get L2 into L2 plus 1 and divided by 2. And plus, then you will get here L2 into L2 plus 1. And here you will get M square. Okay. This is what you have. So therefore, these are the values. So now let us put the values. Okay, L1 is C1. Okay, L1 is 1 and L2 is also 1. So if you put 1 here, you get 2 and 2. And here L equal to 2 we have to put. Okay, so when you put here 2, you get 6. So 6 minus 2 minus 2. So you will get something like this. Here you are going to get epsilon, and here 6, because you are putting L equal to 2 here. So 6 minus 2 and divided by 2. And then here you are going to get 1. If you put 1, you are going to get 2 minus M square. Okay. So this is basically 2 divided by 2. So 1, this is basically, so energy that we have gotten is epsilon, and here 3 minus M square. Now, since L is equal to 2 hai, so M is equal to actually minus 2, minus 1, 0, 1, and 2. These are the M allowed values. So if you calculate M square, you see you are going to get here 2 square, 1 square, and 0. Okay. So basically, you are going to get M square 4, 1, and 0 only. So if you put 0 here, you will get 3 epsilon. If you put 1 here, you will get 2 epsilon. And if you put 4 here, you are going to get minus epsilon. So these are the energies. Okay. 3 epsilon, 2 epsilon, and minus epsilon. Okay. So this was a quite straightforward question related to addition of angular momentum. Okay. In quantum mechanics. Moving to another question. See, it says radius of charged sphere varies with time like this. Okay, so there is a charged sphere. Its radius r. Radius is something r. Let's say radius is something. So it is given to be r plus a and cos omega t, and its charge density was given to be uniform. Okay, so when this sphere actually oscillates, what actually happens is that its dipole moment, see, its dipole moment doesn't change. Okay, I think that's what will happen. See, this is spherically symmetric situation. Okay, so its dipole moment is zero. If dipole moment is zero, okay, yeah, on oscillation also its dipole moment remains zero. Okay, so therefore power emitted by it should be zero actually. Okay, so I have not gone into much details. Okay, but this is what actually appears to be. Okay, so after the original question paper comes out, okay, then we can analyze it in details, but this is what actually I think. Okay, this should be the answer. Now another question, see here, it says a point charge kept inside a conducting sphere of radius capital R is shown in figure. Calculate electric field at this point. Okay, see here, there is a conducting sphere, isolated conducting sphere, and a charge is kept here inside it. So actually what happens when you put a charge inside a sphere, okay, it doesn't matter when you put where you put a charge. Actually what happens, a minus q charge gets induced on inner surface and plus q charge gets induced on the outer surface, and plus q actually remains uniformly distributed, okay, on the outer surface. This minus q is not uniformly distributed here. There will be dense negative charge. Okay, this side will be less dense negative charge, but plus q is uniformly distributed. And what actually happens, is that uh, outside field is determined only by outer charge, not by these inner charges. Okay, so irrespective of where this charge is, field outside is only determined by outer charge. Okay, and outer charge is uniformly distributed, so therefore this is where outer charge will behave as if the outer charge is concentrated at the center. Okay, so the distance of this point from center is actually b, so that's why electric field will be simply q upon 4 pi epsilon naught and b square, and direction will be x cap. Okay, so that is the answer. Okay, in this case, field is decided by only by outer charge, not by inner charges. All right, now another question, it says, see, a rocket crosses origin at t1 equal to 0 and x1 equal to 0. Okay, so there is, so crossing of rocket is being called event 1. Okay, so they suppose this is origin, a rocket crosses it, so that is being called event 1. So event 1 occurred here. This is what I think is the question. Okay, so event 1 occurred here. Now observer at origin sends signal towards rocket at t2 equal to t and x2 equal to 0. So event 2 is this, यहाँ से एक signal ऐसे भेजा जा रहा है, signal is being sent. This is rocket, suppose has reached this position now. So this is rocket. Rocket is moving in this direction with speed 0.5 c. Okay, so signal is coming with speed c and rocket is going with this speed, and since it is sending signal at time t equal to capital T, by that time rocket must have traveled a distance 0.5 c into t, distance equal to speed into time. So rocket has traveled this much distance. So now gap between a rocket and light pulse is actually 0.5 ct. So light pulse will be able to, its speed is higher, so it will catch the rocket. Okay, so it will catch the rocket after time, duration, that we can calculate, that will come out to be 0.5 ct, and divided by difference of their speed. Okay, so that is also 0.5 c. So this cancels out, so you get t. So therefore this light pulse will reach rocket after this much time. After means after it starts from here, so therefore it will reach the rocket. Then at that moment time will be, because rocket, this light was itself launched from here, light pulse was sent from here at time t equal to capital T, and it will take another time capital T to reach the rocket. So therefore total time spent will be 2t. So light pulse will reach rocket at time 2t. Okay, and at that moment rocket, because light is taking capital time, sorry, rocket is taking time capital T, so in that duration rocket would have also moved a further distance, speed into time, so 0.5 c into t. So it was already 0.5 c into t, and another 0.5 c into t it has moved. So therefore light pulse will reach rocket, okay, at the at a position which is equal to 0.5 c into t, and again again 0.5 c into t, so that is actually c into t. So this will be the position where light pulse will reach the rocket. Okay, so this was a very basic question. Okay. So therefore, if you call reaching of light pulse or catching of light, light pulse reaches the rocket, that you call event 3, then coordinate and time of event 3 will be equal to this much. Okay, 2t and x3 equal to ct. So that's the answer. Now, it says there exists this is a question from magnetostatics actually. See, it says this is suppose xy plane, and there is a small bar magnet here. Okay, this bar magnet has magnetic moment in this direction. Okay, so question says there exists a magnetic field. Magnetic field is in z direction here. You see, magnetic field is b. It is a function of x, and its direction is z cap. Now, bar magnet is kept on xy plane with its magnetic moment pointing in y direction. How will magnet rotate and translate? Okay, so here you see magnetic moment is in this direction, magnetic field is in upward direction. So torque, initial torque, if you calculate, see T initial. Okay, T initial, if you calculate, it will be m cross b. Okay, so m j cap and cross b is actually b and k cap. So j cross k is I cap. So m into b and I cap. Okay. So torque, initial torque is in I cap direction. That means I cap will act like axis for its rotation. Okay. So because of the torque, this bar magnet will rotate, and I direction will act like an axis. So it will rotate like this. So it will rotate. We can say that since this I direction is acting like axis, torque is in this direction. Okay. So it will rotate like this. Okay. M cross B, you can see using cross product also. M is in this direction, B is in this direction, so M cross B. So it will rotate in this sense. Okay, so we'll say it will rotate. It will rotate in YZ plane. ये YZ plane में rotate कर जाएगा. It will rotate in YZ plane. Okay. Now, after some time, see, it will be in YZ plane, so it will have a magnetic moment, will have magnetic moment will be pointing something like this. Okay, so it will have a component in Y direction as well as Z direction. So if you calculate potential energy, we write minus m dot b. Okay, so we'll have so when we calculate potential energy, see, we minus m, and so m has some component in y direction, mj, myj, and mz k. And since magnetic field is k in k direction, so we can write this is mz. So m will have some component in z direction after some time. Okay, so minus mz and b, that is the potential energy. Now, since this is a function of x only, so we can calculate fx is equal to minus du by dx. So that will be mz and dv by dx. This is not zero. This is not zero. So this bar magnet will later on experience some force in x direction. So that's why it will translate in x direction. Okay. But if you calculate force in y direction, see del u by del y, see this magnetic field is not function of y, so force in y direction is 0. Similarly, force in z direction will be 0. So magnet will not translate in y or z direction, it will translate only in x direction. So we can say that it will translate in x direction. Okay. Now, another question. See, it says 4 distinguishable particles are distributed in 3 energy levels. Okay, so there are 3 energy levels. Here, there is 0, there is epsilon, there is 2 epsilon. Okay, and there are 4 distinguishable particles, A, B, C, D. So these are distinguishable particles. Okay, so distinguishable particle means we can rearrange them among themselves. Okay, and get a new configuration. So therefore, here we want number of microstates having energy 4 epsilon. So E total is fixed here. E total is actually 4 epsilon. So for getting this E total, how we can distribute the particles, okay, among these energy levels. So see, we have this kind of situation. We can put 2 particles here, A, B, and 2 particles here, C and D. Okay. So two particle here and two particle here. Okay, so therefore you see, if you put two particle here, you will get total energy 4 epsilon. Okay, and for this total energy 0, so total energy will be 4 epsilon actually. Okay, but two particle can be put here in actually. See, these two particles can be put here in actually 4C2 ways. So that is 6 ways actually. Okay, because so there will be 6 such configuration. Okay, for example, if you put A and B, then you can put A and C and A and D. Okay, then B and C and B and D. Okay, then C and D, like this. So there will be total 6 configuration. Okay, similarly here there will be another configuration. Suppose you put here two particle A and B here, and one particle C here, and one particle D here. So here again, see, this you can do in 4C2 ways, and C and D can be, suppose AB is here, then C can be here and D can be here. Okay, so there are two configurations: D is here, C is here, or C and D can be exchanged. Their positions can be exchanged because they are indistinguishable. Sorry, they are distinguishable. So that will give another factor of 2, because there is C and D can be arranged by in factorial 2 ways. Okay, so this will give you 12. Okay, and now so here also, see, you put two particles, then for one particle energy is epsilon, for another particle also energy is epsilon, and for this particle energy is 2 epsilon, so total energy is 4 epsilon. Okay, now what one thing we can do, we can put all the particles here, A, B, C, D. Okay, and no particle here, no particle here. Okay, so this can be done in only one way. Okay, so there is one way for this. Okay, so you can check. I think there is no other possible configuration for this. Okay, so total will be 19. There are total 19 ways, okay, in which you can distribute particles and get total energy equal to for epsilon. Okay, so there are number of microstat is actually equal to 19. I think I have not made any mistake. All right, now let's do another question. See, here Lagrangian is given, and question says conserved linear momentum. Actually, my mic is switching off. Okay, so if mic switches off, I'll take a pause and then come back after some time. So here question is there is Lagrangian, okay, and in option some combination of velocities was given, okay, and question was which is the conserved linear momentum. Okay, so what we can do is here, see, if this, suppose these things in option some quantities were given, and question is which is conserved. So suppose something is conserved, then its total time derivative must be 0, and suppose you calculate its total time derivative, then you get here 2x double dot and plus y double dot and plus z double dot. This we have to, if we can prove that this is 0, then this will be conserved actually. Okay, so for that we need x double dot, y double dot, and z double dot. That comes from equation of motion. So we'll write here x equation of motion. Okay, so that is d dt of del L by del x dot and minus del L by del x, that is equal to 0. So let's differentiate. When you differentiate it with respect to x dot, you get 2x dot, 2 and 2 cancel out. And again, you differentiate with respect to t, so you get here mx double dot. And minus and this minus becomes plus, so you get here 2 alpha, that is equal to 0. So you get here x double dot is equal to minus 2 alpha by m. Already question number 1. Okay. Now, similarly, y equation of motion, we will get here d dt of del L by del y dot minus del L by del y equal to 0. Now, again, let's differentiate with respect to y dot. So when you differentiate with respect to y dot, you get here z dot actually. Z dot divided by 2. Here there is 2 also, and m also, obviously. And this side you are going to get plus, when you differentiate with respect to y, you get 3 alpha, that is equal to 0. So when you differentiate this, you get from here z double dot is equal to minus 6 6 alpha upon m. Let's call it equation number 2. And now z equation of motion. So when you write, this is d dt of del L by del z dot minus del L by del z equal to 0. Okay. All right, so now let's differentiate with respect to z dot. See, z dot is in two places. So when you differentiate it, first term gives you y double dot divided by 2 plus second term gives you z double dot, because 2 factor will cancel out with this factor. Okay. And there is factor of m also, plus this side you get here alpha, that is equal to 0. So when you do the calculation, we put z double dot from here. Okay. So this is minus. So 6 alpha by m we will get from here, and so m and m will cancel out. So minus 6 alpha plus alpha minus 5 alpha. So y double dot you are going to get is basically for 10 alpha by m. You can check here 5 and this 2 gets multiplied, so 10 alpha. So now let's check, let's put all the values here in this one. 2x double dot, see x double dot we have gotten to be equal to minus 2 alpha and by m, and plus y double dot we have gotten that is 10 alpha by m, and z double dot we have gotten how much? This was z double dot was somewhere, this was minus 6 alpha by m. Yes. So now you see minus 4 alpha and minus 6 alpha, 10 alpha and 10 alpha cancel out. So this is 0 actually. So we are getting total time derivative of this quantity. If you calculate total time derivative of this quantity, okay, we have differentiated it. So we got this, and when we put the value of x double dot, y double dot, z double dot, it is coming out to be 0. So therefore we can claim that this quantity is conserved. Okay, it is conserved actually. Okay. Moving to another question. See, this is a question from generating function. Okay, I think I take a pause here and charge my mic for some time. Then I'll come back. So let's. Okay, so now this is a question from generating function. See, in this question, this generating function is given. Okay, and some other information was also given. Okay, but suppose we do not use those information. Okay, then also roughly this question can be solved. Okay, what we can do is, see, this is generating function, it is function of p and q. Okay, so we can write del psi upon del p is equal to q with negative sign. Okay, but there will be a negative sign here. But if you use the other information that was given in the question, then you are actually getting positive sign here. Okay, so that is the use of the extra information given in the question. Okay, so that is giving us a positive sign here. Otherwise, generally we get a negative sign here. And q, capital Q, see, it is a function of capital Q, so we can differentiate this generic function with respect to capital Q, and we get here capital P. So again, we are actually getting positive sign here. Generally, we get negative sign, but extra information is making this negative or converting this negative into positive sign. Okay. So here, let's do the differentiation. So when you differentiate it, you get P by omega, and here tan 2 pi and capital Q. Okay, let's call it equation number 1. Okay, and when you do differentiation here, you get here p square by 2 w 2 omega, and this 2 pi, there will be factor of 2 pi, and also we get here sec square and 2 pi q, 2 pi capital Q. All right. So now you see capital P is given here, capital P is given. So what we can do is we can put the value of capital P here. Okay, so capital P, if we put here, we get omega upon 4 pi and t square, and that is equal to here p square upon 2 omega and also 2 pi. Okay, so 2 and 2 actually cancel out, and here we get sec square, so 1 by this is cos square 2 pi q. So from here you do cross multiplication and you can obtain p. So that will come out to be, see, this 2 and 2 will cancel out, and pi becomes pi square, and omega becomes square. So all terms become square actually. So when you calculate p, you will get here omega and upon 2 pi and t. Okay, and here you will get cos 2 pi q. That's the value of p. Okay, that we are getting. Now we can put the value of P here to obtain Q. So put into 1. Okay, so that gives us Q here. Q will be equal to, so we are putting the value of P here. So omega and omega will cancel out. So we'll get here T upon 2 pi, and tan can be written as sine by cos. So cosine will cancel out. So we'll get here sine 2 pi Q. So these are the answers, this and this. Okay. Now, next question. See, it says for Balmer series of hydrogen and deuterium, calculate this lambda h minus lambda d. This is for hydrogen, wavelength emitted by hydrogen, and this is wavelength emitted by deuterium. See, hydrogen, we know that hydrogen consists of electron and proton, and deuterium, it consists of electron and proton and neutron. Okay, in nucleus there are proton and neutron. So basically here, if you say there is mass of electron and there is mass of proton. Okay, here there is mass of electron. Electron is moving around the nucleus, and in nucleus we have mass of proton and mass of neutron. So effectively we can say we have mass of twice the mass of proton. Okay, so wavelength, if you if you read the theory, you will notice that wavelength is inversely proportional to reduced mass. Okay, so therefore if we calculate this term lambda h minus lambda d upon lambda h, we will get here 1 by mu h minus 1 by mu d upon 1 by mu h. Okay, so therefore this becomes mu d minus mu h upon mu d. So let's calculate it. See, here we get mu d. Mu d is basically d. Deuterium is made of basically electron is revolving around nucleus, which mass of nucleus is twice the mass of proton here. So here reduced mass will be me into twice of mass of proton. Okay, and divided by me plus twice of mass of proton, minus here me and here mass of proton divided by me and plus mass of proton, and divided by here me into twice of mass of proton and divided by me and plus twice of mass of proton. That's what we have. Okay, so me can be cancelled from all. Okay, so here from numerator and denominator take 2 mp common, so 2 mp 2 mp will cancel out, and what you will get is actually, see, 2 mp, if you take common, you will get 2 mp, and here you will get me divided by 2 mp, and I'll take it to numerator, so its power will become minus 1. Minus, similarly here take mp common. Okay, so when you take mp common, mp will cancel out, so here you will get 1 plus me by mp and whole power minus 1, and divided by here again to take 2 mp common, so you will get here 1 plus me upon 2 mp whole power minus 1. Now do its binomial expansion, so you will get here 1 minus me by 2 mp, okay, minus 1 minus me by mp, and this whole term is divided by 1 minus me by 2 mp. Okay, so here 1 and 1 will cancel out, and this is minus minus plus me by mp, and here you get minus me by 2 mp. So when you subtract, you get here me by 2 mp with positive sign, and here you get 1 minus me by 2 mp. So here you can neglect this term in comparison to 1, so roughly we get here me by 2 mp. So what we had to actually calculate is this multiplied by 100. So when you calculate this lambda h, so lambda h minus lambda d divided by lambda h into 100, you get here me divided by 2 mp multiplied by 100. So here this is me, and 2 times mp, mass of proton, is actually 1840 times mass of electron. Okay, and this is 100. So we get here 1 divided by, you can divide it by 100, you can bring this here. So it will become 36.80. So you can calculate it. It comes out to be close to 0.03. Okay, so that's the answer. This is coming out to be positive. Okay, so that is the answer. Now let's move to another question. The another question is related to statistical mechanics. It says Hamiltonian of a system is this, where sigma can take values -1, 0, and +1. So we have to calculate this is magnetic moment or magnetization. So we are differentiating magnetic moment with respect to h and dividing it by n. Okay, and we are also taking limit h tending to 0. Okay, so here, see, first of all, let us calculate energy of the system. If you put sigma equal to -1 here, this term becomes 0, and here minus and minus plus, so you get energy is equal to mu b into h. Okay, now another energy that you will get, if you put sigma equal to 1, again this term becomes 0, and this becomes minus mu b into h. And if you put sigma equal to 0, this term becomes 0, and from here you will get delta. So these are the energies of the system. Okay, so therefore, if we write here partition function, we get here e to power minus beta e I and summation on I. Okay, so different energies we'll put here. So we'll get here e to the power minus, if you put this one, beta h, and there is mu b. And when you put this one, you will get e to the power plus beta h and mu b. And when you put this one, you get e to the power minus beta and delta. So what you do here, divide by 2 and multiply by 2. So this becomes cosine hyperbolic. So 2 times cosine hyperbolic beta h and mu b, and plus e to the power minus beta and delta. Okay, so that is the partition function. Okay, so magnetic moment per particle we can calculate. Okay, let us call it small m, magnetic moment per particle. So this will be magnetic moment of individual particle and probability of having that magnetic moment. Okay, probability of having that magnetic moment and sum on all. Okay, so this is basically magnetic moment is mu b or into sigma I. Okay, and probability can be written like this, e to the power minus beta ei and divided by z. So summation on all I. So that is the magnetic moment per particle. For n particle, we can just multiply by n. Okay, so let us calculate it. So this mu b is outside, and sigma I, if you put here 1, sigma is 1, 0, and -1. So when you put 0, you won't get anything. So we have to just put +1 and -1 here. So when you put plus, you get a plus sign, and when you put minus, you get a minus sign. So 1 by z will be out. Okay, and for plus sigma equal to +1, you get here. So for sigma, when you put sigma equal to +1 here, you have to write corresponding energy. So for sigma equal to +1, we had obtained here my sigma equal to +1. This is the energy. So you get here minus mu b, okay, into h, and there is obviously beta. And when you put sigma equal to -1, okay, so you get here minus, here minus, and this energy e to the power minus beta mu b or into h. Okay, so this is what we are getting. So what we can do, again, we can divide it by 2 and multiply it by 2. Okay, here you get plus actually. Oh, sorry. When we put this negative energy, and this negative and negative becomes positive, so here we get positive, and when we put positive energy, we get negative here. All right, so that's what we have. So divided by 2 and multiplied by 2, this becomes sine hyperbolic. Okay, so therefore magnetization per particle is this. So if you calculate magnetic moment for, or magnetization for n particles, okay, you get here n into b mu b. Okay, and here this becomes and there is a factor of 2 also here, this becomes sine hyperbolic. Okay, so this is sine hyperbolic beta mu b or into h. Okay, and divided by z, so there is partition function which is here e to the power minus beta delta plus this 2 times cosine hyperbolic beta mu b and h. Okay, now let us calculate 1 by n and delta m by delta h, and here at h equal to 0. So here, when you differentiate it, this numerator by h, Okay, this sine hyperbolic becomes cosine hyperbolic. Okay, and when you put h equal to 0, this will become 1, and this multiplicative factor will come outside. So here you get actually n and n cancel out. So 2 mu b whole square, and there will be a beta factor. This beta will also come out when you differentiate with respect to h. And this sine hyperbolic becomes cosine, and when you put h equal to 0, you get 1 here, and when you put h equal to 0 here, you get 1. So e to power minus beta and delta and plus you get 2. Okay. Now, when you put this, we are doing differentiation with respect to h. So h is in the denominator also. So when you differentiate this denominator with respect to h, you get something, but sine hyperbolic will still be there. So when you put h equal to 0, the sine hyperbolic term becomes 0. So you get actually 0 here. Okay. So answer is 2 mu b square into beta. So beta can be 1 by kbt. Okay. And here it was minus beta delta plus 2. That is the answer. That's the answer for. Now moving to another question. See, this is a question from quantum mechanics. It says for this state, you have to calculate expectation value of h. So here you can see L value cost total power of sine and cosine is actually 2. So L value is 2, but coefficient of iota phi is 1 actually here in the power. So M is equal to 1. We know that expectation value of Lz is actually equal to mh bar. So since M is equal to 1, so answer will be 1 into h bar. So that is h bar. Now another question. See, it says Hamiltonian of a system is this. Find correction to the partition function. We have to find correction to the partition function. Perhaps this question was for spin half system. Okay. So here Hamiltonian is given. H is equal to JSZ. Sorry, J is just a constant factor, and this is SZ and plus lambda, and this Sx can be written as actually S plus S minus and divided by 2. Okay, so that is H. See, it was also given in the question that lambda is much less than J. Lambda is very small in comparison to J. Okay, so here what we can do is, see, this is an operator. So we have to calculate its energies. So what I'm going to do is I'll write its matrix form. Okay, so let us calculate its matrix elements. Okay, so we are going to write its matrix form of this Hamiltonian in SZ basis. Okay, so matrix form for H in SZ basis. SZ basis means we are assuming that SZ has two eigenstates. We are calling it up state. Suppose this has eigenvalue h bar by 2 and it gives you 1. And SZ has another eigenstate which are calling down state, and it has eigenvalue minus h bar by 2, and here you get 2. Okay. So in this basis, if Sx acts, okay, on state 1, we actually get here state 2. You can verify this. Okay. And when Sx acts on state 2, you get actually state 1. These are not eigenstates of Sx. Okay. So therefore, when you calculate here H, 1 element actually, so you write like this 1 H and 1. So basically when Sx, not Sx, I wrote it incorrectly. See here it is, see, when S minus acts on 1, you get S actually state 2, and when S plus acts on this, you get actually this is state 1, and when S plus acts on 1, you get 0, and when S minus acts on 2, you get actually 0. Okay, so now here you calculate H 1 element. Okay, so SZ acting on this gives you 1 here. Okay, and you end up getting here and again you are taking inner product with 1. So here, from here you will get J, and here you see when S minus acts on this 1. Okay, S minus acting on 1, you get 2, and you are multiplying with this side by 1. So 1 and 2 inner product will give you 0. So you don't get anything here. Okay. Similarly, when you calculate H22, okay, you can check that you again get the same thing, J. Okay. And when you calculate H12, you write it like this, 1 and H and 2. So when H acts on 2, SZ gives you actually, see, SZ. Here actually, see, SZ actually gives H bar by 2 here, H bar by 2. There will be H bar by 2 factor here. Because when SZ, I have written here, SZ acting on 1 gives you H bar by 2. So there will be J H bar by 2 and J H bar by 2 here. Okay. Now, H acting on 2, on this side we are multiplying by 1. So when SZ acts on 2, you get 2, and when you multiply by 1, you get 2 multiplied by 1. Inner product of 1 and 2 is 0 actually. So you get 0 here. Okay. So this factor doesn't contribute. But when S plus, you see here, when S plus acts on 2, you get 1. Okay. And also you get here H bar. There is a factor of H bar here everywhere. Sorry. This is 0 actually. So when S plus acts on this is state 2, you get H bar, and from here you get a factor of 2. Okay, and there is lambda. So you actually get lambda by 2 and H bar. Similarly, when you calculate H21 element, you actually get lambda by 2 H bar. All right. So therefore, matrix for this H operator is actually equal to H bar by 2. And here you get J, and here you get lambda and lambda. So now, if you want to calculate its eigenvalue, we are leaving this for the time being. Okay, we are just focusing on this matrix. So we'll write J minus lambda primed lambda, and here lambda and J minus lambda primed. Okay. All right. So that's what we get. I think I made some mistake here. See, when SZ actually acts on state 2, you get minus here. So this is minus actually. This is minus. Okay. Minus H bar by 2. So there is minus sign here. Okay. Minus sign, minus H bar by 2. Okay. So this is minus. That is 0. All right. So now let's calculate this lambda primed, which is eigenvalue. Okay. So let's multiply it. So you get here, when you multiply this, J square minus lambda primed square, and there will be a minus sign common here. Okay. Minus lambda square, that is equal to 0. Okay. So from here, you see, if we do calculation, we get minus J square plus lambda square, lambda primed square, and minus lambda square is equal to 0. So here we are getting J is equal to, sorry, lambda we want to calculate. Lambda is the eigenvalue. Lambda is eigenvalue here. So lambda primed, you calculate from here, you get plus minus root under J square plus lambda square. So there we have got it 2 eigenvalues, J square plus lambda square. Okay, plus minus. All right. So let us, since J is much bigger than lambda, so what we'll do is we'll take J outside. So you get here plus minus J, and here you get 1 plus lambda square by J square power 1 by 2. So since J is very high, very big in comparison to lambda, so we will take variable expansion here. So we'll get here plus minus J, and here 1 plus lambda square upon 2J square. Okay, that's what we have. Okay. Now, suppose this lambda term is not there. Then here SZ eigenvalues are plus minus H bar and plus minus H bar by 2. Okay. So we can easily write the partition function with this Hamiltonian. Okay. Now, because of the presence of lambda, there is some correction to the partition function, and that correction we have to calculate. Okay. So these are the eigenvalues. Okay. So now if we write energy, see energy, we have to multiply by H. We had omitted H bar by 2 here. So we have to multiply it by. So we'll get here plus minus J H bar by 2. And here 1 plus lambda square upon 2J square. So these are the energies. Okay. Now using these energies, we have to calculate the partition function. So let us go to another slide. See here, energies are actually plus minus J H bar by 2, and here 1 plus lambda square upon 2J square. Okay. So let us write partition function. So z is summation e to the power minus beta ei and summation on I. So first e to power minus beta, first energy we are writing with positive sign, beta h bar by 2, and here 1 plus lambda square upon 2 j square. Now plus e to power with negative energy we are writing here. So now this becomes plus beta j and h bar by 2 and 1 plus lambda square upon 2j square. Okay, that is the energy. Okay, so here we can write e to power minus beta j h bar by 2 and e to the power minus beta, and 1j will cancel out. So lambda and h bar divided by 2j, sorry, 4j will get here, 4j plus e to the power beta j h bar by 2 and e to the power, when you multiply these two, you get beta lambda square h bar upon 4j. Okay. So now here we will do its expansion. We know that exponential can be written like this, 1 plus x square by factorial 2 and so on. So we are neglecting higher order term. We are using these two terms only. Okay, so e to power minus beta j h bar by 2. And here you get 1 minus beta lambda square h bar by 4j plus here e to power beta j h bar by 2. And here you get 1 plus beta lambda square h bar by 4j. Now you see here, there is negative sign and there is positive sign. So therefore you are most probably going to get sine hyperbolic term. Okay, so let us write first term. Okay, so e to power minus beta j h bar by 2 and plus e to power minus, sorry, yeah, plus beta j and h bar by 2. And here when you multiply, see these two terms are same actually, so we can take them common, beta lambda square h bar and divide by 4j, and here we will get e to power beta j and h bar by 2, and from here we will get negative sign e to power minus beta j and h bar by 2. Okay, so divide by 2 and also multiply by 2. Okay, so now you see here e to power, this term is the partition function that we would have gotten when there was no lambda term. If this term were only present, okay, then in that case the partition function would have been this term. Okay, so we will call it, let us call it z naught. So we are getting z equal to z naught. This is only because of the sz term. Okay, and because of or j term only. Okay, because of lambda term we are getting this extra factor beta lambda square h bar by 2j, because this 4 and 2 cancel out, and this here we get sine hyperbolic beta j h bar by 2. So that's the answer. Okay, so this factor is actually correction to the partition function. Okay. Okay, next, this is 20th question. It is related to Fourier series. So this is a function plotted. Okay, and question was that which lowest harmonic actually vanishes. So question is which lowest harmonic vanishes. That was the question. Okay, so here you see this is a periodic function. It is repeating from here to here. You can see after this interval it is repeating itself. Okay, so here you can take difference of the two, it comes out to be t. So periodicity of this function is t actually. So here if we calculate, suppose we are calculating bn. Okay, so bn is actually 2 by t, and here we'll have to integrate from 5t by 6 to 11t by 6 and function f of t, and here we'll write psi 2n pi t upon capital T and dt. But here when you integrate 5t by 6 to 11t by 6, see this function is non-zero only from this to this limit, and after that it is 0. So there is so therefore we'll put function to be equal to v naught here, in this interval, and rest of in rest of the interval it is 0. So therefore we don't have to write for that, okay, that interval. So here we'll write 5t by 6 and 2 here, capital T, and this function is v naught in this interval, and here we have sine 2n pi small t divided by capital T and dt. Now let's integrate it. So when you integrate sine function, you get minus cosine. Okay, so to absorb minus, we'll put lower limit first and upper limit later. So, and you have to divide by this factor 2n pi by t. So t and t will cancel out, and 2 and 2 will also cancel out. So you will get here actually bn is equal to 1 by n pi. Okay, I'm sorry, there is v naught also. So there is v naught, this v naught, and here you get cos term, cosine, and lower, let's put lower limit here. So when you put this here, you get this gets cancelled out. So we get here 5 n pi by 3. Okay, 5 n pi by 3, and minus when you put capital T here, t and t cancel out, so you get cos 2 n pi. Okay, so now cos 2 n pi is 1 actually. This is 1, and this will become 1 when n is equal to 6. So when you put n equal to 6, you get bn equal to 0. Bn equal to 0. That means b6 is equal to 0. Okay. Similarly, when you calculate an, that means so bn is basically coefficient of sine term in Fourier series, and when you calculate coefficient of cosine term, you will get something similar, b upon n pi, and here only you will get sine term, sine 5 n pi by 3 minus sine 2 n pi. So this term is actually 0, and here you see if you put n equal to 3, you get a3 equal to 0. So if we put n equal to 3, a3 is 0, but b3 is not 0. If you put 3 here, cos 5 pi is -1 actually. Okay, so b3 is not 0. Okay, so third harmonic will still be present. Okay, but if we put n equal to 6, we are getting b6 0, as well as here if you put n equal to 6, you get 10 pi, and 10 sine 10 pi is 0. So here a6 is also 0. So we can say a6 is 0 and b6 is also 0. So sixth harmonic is absent. Okay, so the lowest harmonic which is absent is actually sixth harmonic. Okay, so correct answer for correct answer should be 6 actually here. Okay. There were some mistakes also in this paper. Some questions were wrong. So I'll discuss about wrong questions in next video. And as I mentioned earlier, this paper was slightly on tougher side. So cutoff is not going expected to be high. Cutoff will be, I think, around 80 for JRF. And for LS, it should be somewhere around 70. Okay, LS. This I'm talking about general category. So that's all in this video. In next video, I will discuss about wrong questions that were in this video in this examination.